Welcome everyone to another tutorial for MAIS 202, and I guess just for MAIS in general. Today's tutorial is about PyTorch. PyTorch is a really important library to understand, or at least something similar to it. So there are other things like TensorFlow and JAX that kind of do similar things, but PyTorch is kind of the one that's used the most in research as far as I'm concerned. So it's really useful to understand. Um, Big picture idea, PyTorch is basically a library that lets you build neural networks without having to worry too much about a lot of the details behind the scenes for training. So things like backpropagation, you don't have to implement yourself with PyTorch. It does it for you. Same thing with gradient descent. That's handled for you. Um, and it also has a lot of nice built-in layers that would be kind of hard to implement from scratch, especially when you get into, for example, convolutional neural networks. These are going to make your life a lot easier, but even just kind of a standard multi-layer perceptron is still quite a pain to code. So PyTorch is going to be a lifesaver for that kind of stuff. Okay, so with that, let's get started. So I prepared a little Google Colab notebook that's also going to be in the description of this video if you want to follow along. We're going to just walk through it step by step. So the first thing to know about PyTorch is that it uses tensors. So tensors are extremely similar to NumPy arrays. So if you haven't seen the NumPy tutorial, please check that out. I'm not going to really explain too much about the tensors in PyTorch just because they're so similar to NumPy that if you understand NumPy, then the PyTorch stuff is going to be kind of almost trivial. Basically, all the methods and stuff are going to be almost the exact same. Sometimes they'll have a slightly different name, but they behave in very similar ways. So I'm going to import both Torch and NumPy. And I'm going to show you how to build a PyTorch tensor. So the first way to do it, just like in NumPy, is to start with a Python list and then pass it to a constructor. So here it's torch.tensor, then we pass as input our data in this list, save it in a variable called x. If I run this cell, it's going to display the output. So again, like I said, torch tensors are basically like NumPy arrays. So we get as output this matrix looking thing with the numbers 1, 2, 3, 4 from our Python list. The next way, kind of unsurprisingly, is we can directly turn a NumPy array into a PyTorch tensor. Okay, so here I make a NumPy array using the data that we defined earlier. I feed it into torch.fromNumPy, pretty easy name to remember, and we run that, and we get the exact same tensor as output. Another way is to build one from an existing tensor. So one convenient function that might come up is torch.onesLike. Basically what it's going to do is it's going to make a tensor that consists only of ones in the same shape as the input tensor. So it's going to have the same shape as here we're feeding as input x. So it's basically going to be a 2 by 2 matrix, but every element is going to be a 1. We also have rand-like, which is just a random tensor, again, of the same shape as the input. And you can also, here I'm just showing, you can also specify the data type that you want the output to be in. So here we're doing torch.float. Float is like well, it stands for floating point number, but basically it means like a continuous number. So not just an integer, but things like 1.2, 3.7, negative 0.25, anything like that. Right? So let's just print the output of the cell. It's going to print both of them, ones tensor and the ones tensor, and then random tensor, and then the actual tensor itself. Okay, so kind of predictable. Of course, we're not limited to just 2 by 2 matrices. We could do this with any type of tensor. Tensors can be just like in NumPy with any number of axes. So not just 2 axes, like in this case, we'd have 3, 4, 5, 6, 7. When I say axes, I mean dimensions, right? So yeah, vectors are one-dimensional, or they have one axis. Matrices have 2, and then 3D tensors are, well, they have 3 axes, and then we can scale up to any number of axes that we want. So in the same way as NumPy, we also have kind of the standard attributes that come up. So things like the shape of a tensor, you can print that. D-type is going to be your data type. And then device is something new, which we're going to go over in just a minute. And actually, let me just change this. Actually, yeah. I'm just going to change the runtime to CPU for this example. For those that don't know, in Google Colab, you can modify your runtime type. So this is basically Google Colab doesn't actually run on your computer. It runs on a computer in the cloud and then sends the kind of output back to your screen. Okay, so if I put it on CPU mode, it means the computer I'm running on is using a CPU. And I also have the option of using GPUs instead. GPUs are graphics cards for computers, and they're much more efficient at computing code, especially for machine learning, because they can do things in parallel. So anyway, we're going to start with a CPU, and then I'm going to change the runtime to a GPU later. I think because I changed to CPU, I'm just going to have to rerun all these cells real quick. So this will just take a second. Okay, so now when I run this, the last line will say that the device is CPU. And it's because we're running our code on a CPU. Okay, so it says device tensor is stored on is a CPU. So this is basically what we're doing our operations on. But it turns out that we can actually change this if we want to be a GPU. Okay, so here I have a line that's basically going to check what device is available. So are we on a CPU or are we on a GPU? And if we're on a GPU, we're going to use this platform called CUDA. CUDA is basically the thing that we use to optimize code on GPUs. So if CUDA is available, it basically means we're using a GPU. So if I run this and I print out the device, currently it says we're on the CPU. But now if I change my runtime type, so we'll do change runtime type and change it to a GPU. Again, I'm going to have to rerun all the cells. And I run this stuff from the top. So we're just getting our tensors. I'm going to have to run everything from up here. So it's going to take just a second to do that. But if I come back here and I run this, our device is still CPU by default. So tensors are always put onto the CPU by default. But now we can check if CUDA is available, which it should be if we're on GPU, which we are. And so this line will hopefully print CUDA. Perfect. So what this allows us to do is if we want, we can actually explicitly move our tensors to the GPU so that our operations on them are much faster. Now, something to keep in mind is that if we want to do operations between two tensors, so for example, add them together, we have to ensure that they're both on the same device. Otherwise, we're going to run into issues. So if we want to add them up, they either both have to be on the CPU together or always be on the GPU together. Okay? So again, the device from earlier by default is set to CPU. But what we can do is tensor.toDevice. So really, right now, if you remember, our device was set to CUDA. So we're going to do tensor.toCUDA, and that means move it to the GPU. And if we print it, it'll just show that our tensor is now on CUDA. Okay, so basically the point of all this, and this is the big difference from PyTorch, remember that the context I brought this up in is that our tensors have kind of a lot of the same attributes as NumPy arrays do, right? They have the shape, they have the D type, but they also have device. That's the new thing that we didn't really have in NumPy. But device is actually going to be really useful because when we're training our neural networks, we're going to want to move all our tensors over to the GPU so that training gets a lot faster. Okay, so and the way we do that is by taking whatever tensor we have and using the .to and then the name of the device we want to move it to. So if we're using a GPU, it's going to be CUDA. Okay, and this line of code up here is very standard. I recommend putting it in your code. Basically, it allows for your code to be device agnostic. So this is going to check if CUDA is available. And then depending on whether it is, it'll either set it to CUDA or CPU. So this means basically your code will run regardless of whether you're on CPU or GPU. But if you are on GPU, it'll make sure that your code uses the GPU and moves your stuff over to the GPU. So when you do .toDevice, it'll move stuff to the GPU after you run this line of code. So this line and then this line will move stuff to your GPU, assuming you're on a GPU runtime. Okay, let's get into some more operations. So again, these are very similar. So if we have two tensors, so x and y, these are both just 2D matrices. We can add them, subtract them, multiply them, divide them. All of these operations will be element-wise in the exact same ways that we do for NumPy. Okay, so addition, subtraction, multiplication, division, exactly what you'd expect. Let's sanity check this. If we added x and y, we should get 1 plus 5, which is 6 is the first element, 2 plus 6, which is 8 here, 3 plus 7, which is 10 here, and then 4 plus 8, which is 12 here. So beautiful. That's what we expect, right? And you can verify the other operations for yourself. But the point is we can basically do anything that we were doing in NumPy. So again, if you haven't seen the NumPy tutorial, go back, watch that, and then all the tensor stuff will feel super natural to you. If this doesn't feel natural, go back, check that out. Okay. There's also broadcasting. Broadcasting is something we spent a while on in the NumPy tutorial, which again, I'm not going to review. But basically it allows for the code to automatically reshape stuff so that we can combine them together in a convenient way. So here what we have is basically a matrix. So A is a matrix containing, what's the best way to do this? Maybe I should display it like this just so you can see. So A is a 2 by 3 matrix, and B is just a vector, a row vector of length 3. And what we want to do is add B to each row of A. And with broadcasting, that's super simple. We just have to make sure the shapes kind of align in the right way with the same rules as NumPy. If we run this, we'll get the result we want, right? So 1, 2, 3, we added to that 10, 20, 30. So we get 11, 22, and 33. And then for our second row, we added 10 to 4, 20 to 5, and 30 to 6. Okay, so hopefully none of this is new, but it's just good to know that all of this stuff still exists in PyTorch. Okay, now we're going to get into the real power of PyTorch. So the first power, which is very important, is the device stuff I went over earlier. So moving all your tensors over to the GPU so that you can run your operations there a lot faster. But really the big one is this thing called automatic differentiation. And the motivation for this, so automatic differentiation means automatically computing derivatives. Okay, so PyTorch will automatically compute derivatives for you. Why is that useful? After the lecture on neural networks, hopefully this is a little bit obvious. The point is you're going to have to do, well, if you didn't have this, you'd have to do backpropagation from scratch. And automatic differentiation makes backpropagation a lot easier for you. So let's look at a really simple example of how we might compute a derivative in PyTorch. Realistically, this isn't something you're actually going to do in practice, but it's nice to know how this works behind the scenes. Okay, so let's suppose we have the function f of x equals x plus 2. Okay, so this is just a line, right? A linear equation with a bias, or sorry, an intercept at 2, right? And a slope of 1. So f of x is x plus 2. And we want to compute the derivative evaluated at 3. Okay, well, if you know your derivatives, this is pretty easy to compute. You probably don't need any fancy software to do this. The slope, right? The derivative is the slope. The slope of this is 1, so the answer should be 1, right? So using our derivative rules, f prime of x is just 1. Hopefully that's easy to see. And then that tells us that the derivative evaluated at 3 is 1 because the derivative is 1 everywhere. Okay, but let's do this in NumPy, and we're going to take it step by step. So first, let's define our inputs. So remember, we wanted to check what the function evaluates at x equals 3. So that's this line. So we're defining a tensor. The value held inside the tensor is just the number 3. And we have this kind of mysterious thing, which I'll explain in more detail, a lot more detail later. But requires grad equals true. Requires grad is short for requires gradient. If you remember from the lectures, a gradient is the same thing as a derivative. Okay, so basically what we're saying is this is a tensor that requires us to compute derivatives. We want to be able to compute derivatives with respect to this tensor. That's what we're saying. Okay. Now a is just going to be a variable to hold the number 2. Okay, the number 2 from here. And 2 is just a constant, so requires grad we're going to explicitly set to false. Okay. I believe by default requires grad is false. And now let's define the function. So f is equal to x plus a, in this case a equals 2. And now here's where the magic happens. After we've computed the result and stored it in f, we run f dot backward, okay? And what this is going to do is it's going to store the derivative inside of x. Specifically, x has an attribute called x.grad where we're going to store the result. Okay, so if this worked, then the value stored inside of x.grad should be 1. Okay, so it's the derivative of f with respect to x. Okay, so let's run this and see if it works. Of course, I know it's going to work, but let's check it out. So indeed, it says the derivative at x equals 3 is 1. So this is cool, right? Basically, somehow, by just combining these tensors together, our code has automatically computed what the value of the derivative is at our chosen x value. And if we wanted to, we could have set requires gradient equals true for a as well, and we could have gotten the derivative of that as well. Okay, so let's break this down a little bit and understand what's actually going on here. So first, as I pointed out earlier, there's something special in the way that we initialize x, right? We added this extra argument, requires grad is true. And basically what this does is it tells PyTorch that the autograd engine, so autograd engine is what PyTorch uses to automatically calculate gradients or derivatives, so autograd, automatic gradients. Basically it tells that engine, so engine is just kind of, you can just think of it as the code, okay? It tells the PyTorch code that it should record all operations that x is involved in. Okay, so it's going to save them somewhere. It's going to remember, for example, we computed f using x. Okay, so PyTorch is going to remember that because we told PyTorch that requires grad is true on x, right? So when requires grad is true, it's saying remember every time we involve x in some sort of computation. Okay, and that will let us go back and then compute the gradients of those operations afterwards. So next we defined f in this way, pretty straightforward, but the key thing to understand here is f is itself another tensor, right? F is equal to x plus a, but x is a tensor and a is a tensor, so f is just another tensor, right? We're just adding two numbers together. Two numbers added together gives you another number. But the key thing to understand here is that requires grad equals true is a contagious, attribute, meaning if f is equal to x plus a, and anything involved here, so x has requires grad equals true, then so will f, okay? So the way I phrase it down here is, since x has requires grad equals true, all of its children will also have requires grad equals true. So that means anything that we define, which depends on x, will also have requires grad equals true. Okay, so let's check it out. So f, my claim here is that requires grad will be true for f, because we computed it using x, which also had requires grad equals true. And indeed, it's true. Okay. So what does that mean? Well, remember, when requires grad equals true, it means we track every operation that variable is involved in, right? So in this case, it means track all the operations that f is involved in. And in particular, the way that this is done is using a computational graph. So it's basically a graph showing the dependencies of variables on each other, okay? So what is this graph we're looking at here? I'm just going to zoom out a little bit so we can see it. So this is what the graph looks like before calling f dot backwards. So x and a are the two variables, right, that we added together. So I'm just showing these arrows mean combine these together by adding to produce f. Okay, that's what the graph is saying. Why is it adding? Because I put a plus sign here. If I put a multiplication sign, it would be more multiplying x and a together. Okay, so let's inspect this step by step. So data for x is the value 3, okay, right? Because we had x equals to 3 up here. For a, the value stored inside of it is 2. And for f, it's 5. Why? 3 plus 2 equals 5. Now the next attribute that's interesting is leaf. The idea is that in this computational graph, both of these are leaves, okay? And I kind of make that a little bit obvious by coloring them in green, like the leaves of a tree. And f is not a leaf. So what does it actually mean to be a leaf? Let's go down and read the explanation down here. So x and a are leaf nodes, while f is not. PyTorch considers a node to be a leaf if it's not the result of a tensor operation with at least one input having requires grad equals true. Okay, and everything else is a non-leaf. So basically what it means is A doesn't depend on anything else that has requires grad equals true, so it's a leaf. Same thing with X, but F does, right? F depends on X, and X has requires grad equals true, so it is not a leaf node. Okay, what else do we have? We have requires grad equals true for X. It's false for A, but it's true for F. Why? Because remember I told you requires grad is contagious. So anything produced, basically anything that depends on X down this graph will also have requires grad equals true. And then the grad attribute, which is where we stored the derivative in the end, is initially set to none. So there's nothing stored there, but after we call f dot backwards, we're going to store something in here. Okay? So let's scroll down and see what happens. So when we call f dot backwards, PyTorch is going to traverse this graph backwards, starting from f, and compute the gradient for all nodes where isLeaf is true and requires grad is true, and saves it in their dot grad attribute. So let's just look at this graph and see which nodes in the graph satisfy that property. Okay, so we start here. Is this a leaf? No. So we're not going to compute the gradient for this. Let's go backwards. X has isLeaf is true, good, and it has requires grad true, good. So we're going to compute the gradient and store it in the grad attribute. For A is a leaf, so that's good, but requires grad is false, so we don't compute the gradient. Okay, so that's what PyTorch is going to do. When we call backward, it's going to traverse here and compute the derivative of f with respect to x and store it in grad. Okay, and that's what happens here. Okay, so the only update in the graph is grad, which is now set to 1 because that's what the derivative is. The derivative of f with respect to x is 1. So hopefully that's clear. These are kind of a little bit, these aren't the most important details, but it's really nice to know, in my opinion, what the library you're working with is actually doing behind the scenes. So what dot backward is doing, right? The name makes a bit more sense now. Why was it called backwards? Because we're traversing this graph backwards, okay? So let's look at a slightly more complicated example. So now we're going to have a function that depends on two variables. So g depends on x and y. And we're going to compute, using PyTorch, the partial derivatives. So the partial, if you haven't seen this before, the partial derivative sign, this is the same thing as a normal derivative. But what it tells you is take the derivative. So note that the d looks different here. Usually in derivatives, you just have the letter d. Here we have a lowercase. Well, this thing's called a del. It's called del. And we're going to compute the derivative of g with respect to x, but it's a partial derivative, which means basically just treat every other variable as a constant, okay? So if we take the derivative of this with respect to x, okay, well, we know what to do with the first term, right? We get 3x squared. Hopefully that's not surprising. And the derivative of 2y is a constant, so the derivative of that constant is 0. So we're done. And then for y, we do the same thing. We treat x as a constant and y as a variable. So this is a derivative of 0 with respect to y. And then the derivative of this with respect to y is just 2. Okay, and we want to compute what the value of that is at x equals 3 and y equals 2. So we're going to do the same thing as before. We're going to have x and y. This time, both of them have requires grad equals true, right? Because we want to compute the gradient with respect to each of them. And then we have a. A is just going to represent the number 2 here again. And then we compute g. So g is x cubed plus a, so this is 2, times y. And then we want to compute the gradients, right? We want to traverse that graph backwards. We do g dot backwards, and it's going to store those gradients inside of x and y. So let's run that. The answer is 27 and 2. Can we verify that? Yes, right? So 3 squared is 9 times 3 is 27. And then, of course, the partial derivative with respect to y is always going to be 2. Okay, so again, zooming out, looking at the computational graph, this time what I've drawn is this node represents cubing. Okay, so it takes an input in here and cubes it. So we have x cubed plus a times y, so 2 times y. Okay? And when we call backwards, we're going to traverse this and look for the nodes that are leaves and require grad, and we're going to update the grad attribute to store our gradient. Okay? So we compute it for x and y. We don't compute it for a because requires grad is false. So you might be wondering, again, why should I care about this? Why is this useful? Because when we're training neural networks, we want to compute gradients and backpropagation, right? And it turns out that here we can just do it with a single line of code. So that's great. So let's actually look at like a super basic neural network. It's not even really a network. It's just a single neuron. But let's see how we might implement that in code. Okay, so we'll have this. Sorry, this is actually wrong. It predicts the value a. So our network is going to predict the value a, where a is basically a sigmoid function applied to a linear transformation, right? You've seen this before, I hope. And then we're going to compute the mean squared error. Well, kind of. We're going to compute this, okay? So it's going to be our prediction, a minus the true y value squared, and then divided by 2. Okay, so let's define, we're going to define the sigmoid function in code. So this is hopefully somewhat familiar. And then we have x, y, w, right? And b is our bias term. So these are the things we care about gradients. We care about computing gradients for, right? In backpropagation, we compute gradients with respect to the weights and biases, right? We don't care about gradients with respect to x or y, so we don't have to set requires grad equals true for those. Then z, you know, this is direct translation from the math. And then we define a variable L, which contains this result right here. Okay, so we run that code. I'm just going to print the values stored in those variables in case you're interested. And finally, again, we run L.backwards. So we're going to compute we're going to create our computational graph, and we're going to traverse it backwards to find the gradients with respect to W and B, our weights and biases. Okay, so we run it. W.grad, B.grad. Here are our outputs. You know, maybe you can compute that on your own. I'd say it's probably a pain in the butt to do it. But what does our graph actually look like? So we take x and w, we multiply them together, we add our bias term to get the value z. We take z and we feed it to a sigmoid function. We get an output a, and then we feed a and y into the mean squared error function to compute our loss. Okay? And then again, we traverse this graph backwards and we look for leaf nodes, right, the green ones, and we check, is this leaf, does this leaf have requires grad as true? If it does, we'll compute the gradient, right? Here I didn't actually show what it looks like after backwards, but hopefully that makes sense now. So if we wanted to, we could now build neural networks like this. So we define a function, and then we just update each of the weights using these gradients computed on their own using PyTorch. Okay. With that kind of foundation of how AutoGrad works, how it computes gradients and then saves them inside of tensors, let's actually build a simple neural network and implement backpropagation with gradient descent and see if our network can learn something interesting. So before we get to that, let's just generate a data set. So I'm just going to generate kind of an artificial data set that's going to be nice to visualize and see how well our network is learning. So don't worry at all about this code, but I'm just going to display what our data set looks like, okay? So our data set has a bunch of blue points and a bunch of red points, and somehow we want to learn a neural network that classifies points. So it classifies points, it's kind of going to split our region into two parts. So hopefully we're going to have one part in here that's going to be points classified as being in class 1, so in the red class, then everything outside will be classified as class 0, okay? So our inputs are 2D vectors. X1, X2 is a single input. And then the y value is just either 1 or 0, depending on what the class is. Okay? And the first thing we're going to do is we're currently running, I believe, on a GPU runtime. Yeah, we are. And so what we're going to do to make our lives easier is we're going to move everything to device. Okay? So when we're creating our tensors, we're going to explicitly create them on the GPU. So why is this GPU? Because device is a variable we defined earlier that stores in it CUDA. So basically, if you put in the word CUDA as your device, it's going to try to move stuff to your GPU. It'll only work, of course, if you're actually running on a GPU. If you're running on a CPU, it's not going to work. Okay, so CUDA is really the value stored here. So if I wanted, I could just write CUDA. Okay, and the other stuff is just, let's see, we're setting requires gradient equals true. So actually, what am I defining here before I go any further? These are just the weights and biases of our neural network. So we have two layers in our network. The first layer has its own weight and bias, and then the second layer also has its own weight and bias. Okay? They all have requires gradient set to true because we want to compute gradients with respect to our weights and biases, of course. We're setting the data type of each of them to be float 32. So 32-bit floating point numbers. If you don't know what that is, it's fine. It's just basically saying I want to store continuous values or approximations of continuous values using 32 bits in memory. Okay. So I'm just going to take all those parameters and put them in a list. And then I'm going to define our model. So what does our model do? It's going to be sigmoid of our weights multiplied by our inputs plus our first bias. And then we're going to take that and multiply it by another set of weights. So really probably a better way of defining this, let me just rewrite this, is like, yes, exactly like this suggestion is saying. Beautiful. Okay, so that's probably a nicer way of writing it. Maybe I'll even be super explicit and write it like this. I don't know if I necessarily need to transpose it. We'll see if that's a good suggestion. So that's it. Okay, so that's going to be the prediction made by our network. So we go through a linear layer, then we apply an activation, then we go through another linear layer, and then we apply another activation, and then we return that as our prediction. Our loss function is going to be the same loss we saw earlier, so it's just going to take the difference, square it, and divide it by 2. And then I've just defined a little function here that will compute the accuracy of our network, which will be convenient for later. So let's run that. Remember, we've moved everything to the GPU. Now I'm just going to split our data set into 400 training points, and then the remaining points are going to be dedicated to testing. Okay, so hopefully this all makes sense. I'm just slicing into our data that I generated earlier, so that's the data here. So the Y values are our labels, so that means 1 or 0. Okay, now I'm going to define a training loop. I'm going to use this library here called TQDM. It's a library that lets you just add a progress bar so you can see how far you are in your loop and make sure your training isn't like extremely slow. I'll define a few convenient variables. So our learning rate, so that's parameter and gradient descent. Sometimes it's denoted by alpha or eta or maybe sometimes beta. Epochs, that's the number of times we're going to go through the whole data set. BS is batch size, so just the number of, we're doing mini batch gradient descent, so it's the size of the batches in that. N is the number of data points in our data set. And then I have to find this loop. Don't worry too much about the logic, because in the end, this actually isn't going to be how we train a real PyTorch neural network. Basically, the approach here is I'm going to gradually show you more convenient features from PyTorch. So here's how you do it from scratch if you didn't really know too much about PyTorch, but you knew that you had AutoGrad. And then afterwards, I'll show you some new features that'll make your life even easier, okay? So anyway, basically, we make our prediction using our model function that we defined above, and then we compute our loss, and we average. I'm doing mean because I'm taking the average over the whole batch. And then we call loss.backwards. That's kind of the really key thing. So here we are computing gradients with respect to weights and biases, okay? And then we're going to call torch.nograd. So what this does is it basically tells PyTorch to not compute gradients for a little bit, okay? Basically, it means we're going to be doing operations here that depend on our parameters, but we don't want those to influence the gradients in any way. Because what PyTorch does is it actually accumulates gradients inside of the .grad attribute, and we don't want basically this loop here for gradient descent to affect it, okay? So what do? we're going to loop through each of our parameters that we stored in the list, right? So params are just our weights and biases. Again, don't worry too much. You're not actually going to implement models like this, but it's just interesting to see. And then we're literally just going to subtract from each parameter the gradient times the learning rate, which is exactly what you've probably seen in gradient descent. And then we reset the parameter's gradient to 0 for the next iteration. Okay, so that's something you have to do explicitly. You have to explicitly set them to 0. Okay, so let's run this loop. There's going to be a little progress bar. It's going to be very fast. So it'll take a few seconds. And at the end of this loop, we'll be done training our model for 1,000 epochs. This is just going to make some predictions using our model and then compute the accuracy. So as a number from 0 to 1, so ideally we want an accuracy of 1, which means 100%. Okay, so here we get extremely close, 98%. And now I've written a function, again, don't worry too much about the logic, that's going to visualize the predictions made by our model. So I'm just going to run that, then visualize our model. So what are we looking at here? So the blue and red points are the exact same ones we saw earlier in this version of the plot, but the colors in the background now tell you the predicted probability, according to our model, that points in this region are in class 1. So if something's very close to yellow, it means that the probability is close to 100% that points in here are in class 1. And where it's pinker means there's a very low probability that something's in class 1. In other words, there's a very high probability it's in class 0. So actually, if we look at this decision boundary, our model does a really good job, right? It's predicting that basically everything in here is in class 1, which is correct, and that everything outside of that yellow region is in class 0. We can notice a few points that are probably being misclassified, like this point and this point are probably leading to the almost 100%, but not quite. So they're probably the ones messing up our accuracy a little bit, okay? So we're going to reuse this visualization a few times throughout this tutorial, so hopefully that makes sense, and we'll move on. So that's basically it, though. A short training loop already looks pretty easy, right? We basically just compute stuff with our model, and then have this little loop here that goes through all our parameters and updates them by using gradient descent. So it's going to be like our parameters gradient times its learning rate. Turns out you're not going to have to do any of this stuff, or at least this stuff, because PyTorch has built-in stuff that makes your life way easier, which we're going to see right now. Okay, so I've organized this notebook with kind of sections. So right now the section we're in is basically this one right here. And it's just a list of improvements over our original strategy that are going to make our lives a lot easier. Okay, so the really important module inside of PyTorch, well, there's a bunch of them, but here's a really important one, torch.nn. NN means neural network, okay? So even though what we did earlier, sorry, little hiccup, even though what we did earlier is a lot easier than implementing this from scratch with NumPy, and when I say a lot easier, I mean a lot easier, we can actually make our lives even easier using a couple imports. Okay, so the first one that's useful is torch.nn.functional. So this includes, as the name suggests, a bunch of functions that are useful. In particular, it's going to be activation functions and loss functions, probably some other stuff too, but those are the main things you'll want to see. So I also have a link here if you want to look at it. To the docs. Sorry, it's confirming I want to do it. So we just have a bunch of functions here built in that'll be useful. Maybe you recognize some of these. Relu, you might have seen. Relu, CLU. So here's Relu. Softmax is here. You've probably seen that in class. TANH you might have seen. Sigmoid you've seen. Dropout you might have seen. Probably not. Convolutions, right? 2D convolutions, that's for convolution neural networks. Anyway, we have a bunch of stuff here, a lot of useful stuff. Let's see how it works. So we import it. The convention is usually as capital F for whatever reason. Some examples are sigmoid, TANH, Relu. Some loss functions are mean squared error loss, binary cross entropy loss. we can run any of those. So here I have the output printed of the binary cross entropy loss between these two numbers, these two predictions. Probably if I do this, it'll be a lot better. Yeah. Okay, so those are some nice things we can use. So already in a neural network, instead of defining sigmoid from scratch like we did, I don't know where we did that, we did it somewhere. We can, oh, I'm actually cheating by using torch.sigmoid here. So I should actually really be using the built-in sigmoid from earlier. Pretend I wasn't doing that. But yeah, here we're using sigmoid built in from PyTorch. Okay, the next improvement, again, is from torch.neural network. This time it's literally the whole kind of module itself. And in particular, it's this thing called NN, so neural network.module, which is basically a class that represents a neural network or a model. And whenever you're writing a class to represent your neural network, it should inherit from it. So to inherit, you just do this. And then also in the constructor, you're going to want to run the parents, so the parent class's init function before running everything else. Okay, so that's just kind of standard Python OOP stuff that hopefully you've seen before. If you haven't, just kind of copy and paste this general format at the start. So here we're defining a class that represents a function. We could have called it anything we wanted to. We could have called it banana network or whatever. Here we're calling it simple net to make our lives, it's a good name. Okay, so what does our network look like? Here we're going to have a neural network that takes as input a two-dimensional vector and spits out a three-dimensional vector. Okay, so so this is the first layer, nn.linear, linear layer that goes from 2D to 3D. Okay, so that's not too complicated. And then we're going to have another layer that then takes 3D and maps it back to 1D. Okay, so this is our neural network for predicting, in this case, we're predicting a one-dimensional output, which is going to be our probability of being a class 1 point, a red point. Okay, so how's our network going to work? It's going to pass our input through layer 1. It's going to apply the sigmoid activation function. Then it's going to feed it through layer 2. And then it's going to apply another sigmoid activation function. And then it's going to return the result of that activation. Okay, so we've just defined a class that initializes by creating two layers and then has a forward function, which just means the forward pass through the network. So starting from the input and going to the output. That's it. Okay, so we define a model this way. No need to even define explicit weights anymore. We actually just use nn.linear. This also includes a bias term by default. Okay, so if I really want it to be explicit, we're saying there are 2 in features, 3 out features. We have a secret bias term that's not being displayed. And what else is on by default? Let's see. Probably nothing too important. I think these are the most important things to know. Okay, so again, this has 3 input features, 1 output feature, and has a bias term. Okay? And that's it. So let's define this. And we're going to try to train this model. So first of all, what we're going to do to train our model on the GPU is instead of individually adding each weight to our device, so to our GPU, we can just do model.toDevice. So this is something that comes with inheriting from nn.module. Okay, so we're going to move our model to the device, and here it's just printing what our layer, or what our model looks like. So layer 1 has a linear, 2 inputs, 3 outputs, blah, blah, blah. Stuff I already showed you earlier. By the way, something I actually ignored earlier, in this code that I told you to ignore, one important thing is that we want to move all our inputs of the network to the same device as well. Okay, maybe actually I did that. No, I didn't. Yeah, so we want to move the inputs of the network to the same device like we do here, because like I said, if the weights of our model are on the GPU, then we also have to make sure the inputs of our model are on the GPU so that they can be combined together. Okay. So anyway, where was I? I defined this model, moved it to the GPU. For our loss function, we're going to use the built-in mean squared error loss function. Okay. And now we're going to use another improvement. This is a really big one, is PyTorch's built-in torch.optim. So optim means optimizer. And basically what this is going to do is perform gradient descent for you, or you can use more sophisticated optimization algorithms as well. So if I just go here, torch.optim, you can read all this stuff if you want. I don't know if they have a list of all the optimizers somewhere. Yeah, so they have a bunch of algorithms here. So the classic one that you've seen in class, the kind of simplest one is stochastic gradient descent, but a nice one to use as well is Atom, the Atom optimizer, which is probably not covered in class, but I recommend using that for whatever you're doing. You can find some stuff about it online. Okay, so we're going to import optim, so optimizer from PyTorch. And then here we're just going to use SGD, stochastic gradient descent, and it takes a few inputs. So maybe what I should do again is be a bit more explicit about what the inputs are by using their keyword names. So the first input is parameters, which you can access by just doing model.parameters. So again, model.parameters, why can we do that? It's because we're inheriting from this module class. And what this does is it basically sends to SGD just a list of all the model's parameters. In fact, let's just see what that looks like, model.parameters. So, okay. Here's, hold on, next, later. Pretty sure that'll work. Okay, so here's, or actually, you know what I'll do is for param in model.parameters, print param. So model.parameters is basically a list of parameters stored inside of our model. Okay, so here's our weights for the first layer. Here's our bias for the first layer, I guess. What are we looking at here? Yes, that's right. Okay. So our first layer, right, takes as input a two-dimensional vector and spits out a 3D. So we have this 3x2 tensor. And then the next one goes from 3 to 1. Oh, also this is the bias term for that. And then we have a 3 to 1. So this is our weights for layer 2. And this is the bias for layer 2. Okay. So anyway, that's basically what we're feeding as input for the first parameter of SGD's constructor. Then the second thing is LR, which is our learning rate. So this is the step size during gradient descent. So I think we had it set to 1 earlier. So we're setting it to 1. Of course, it could be more likely probably something like this, or even more zeros. You'll kind of just have to experiment with it. Here we'll use 1, but yeah, like I said, not a very common value to use in practice. So okay, we've initialized our optimizer. So now what does our training loop look like now? So first, what are the inputs? So we're going to define a function to train our model. It takes a few things. So it's going to take our model as input. It's going to take a loss function as input to compute the loss. Our optimizer, which is this thing we just defined above. The number of epochs we want to do. Our X training data, our Y training data, and our batch size. Okay, and the first line that's new is this, model.train. This is something you have to run to basically just tell PyTorch that you're planning on doing some training. So actually, if I run this, I believe now we can see a preview of what this does. Model.train. Okay, it's not showing. Anyway, so you should run this before training. Most of, I think all of this code is exactly the same as before. But what's nice is now instead of having that loop for stochastic gradient descent, we just do loss.backwards to backpropagate the loss and compute all the gradients. And then to update all our weights, we just do optimizer.step. That's it. So this is updating every single weight in a single step using the learning rate that we defined earlier. And then, this is important, we do optimizer.zeroGrad to reset the gradient of all our parameters before we move on to the next iteration, the next epoch, or sorry, the next batch, before we move on to the next batch. Okay, and again, we're using the TQDM progress bar to make our progress visualized in code. So let's train. Should take about the same amount of time, maybe a bit faster even than the one we defined earlier. Okay, and now let's visualize our model. Something we have to do beforehand is model.eval. Basically just tells PyTorch that now, instead of training, we're using our model to evaluate stuff, to make predictions, but we're not updating the gradients anymore. Okay, so model.eval, and then visualize model. Let's see what we get. Okay, so we get a pretty nice decision boundary here. Maybe a bit more accurate than the one from earlier. I don't know, I'm not actually explicitly computing the accuracy. The real takeaway here is we get basically the same model as earlier, but using slightly simpler code in terms of the optimization stuff by using this built-in optimizer. And also the code for our model is a lot easier and kind of more scalable. We can make this a lot more complicated than the old version that we were doing up here, where we define like a model function, and yeah, we have this loop where we go through all the parameters. So this is already a lot better. But it turns out there are a few improvements we can make. So the first thing that's kind of annoying in our code right now is that we have this nasty logic here for batching our data. So basically, in mini batch gradient descent, we have batches of data, and we have this code here that basically kind of does some nasty indexing stuff to slice our data, send it to the GPU. You know, this slicing stuff here is kind of a pain. Maybe you'll make some little mistakes in your computation here. We have this nasty thing right here for finding the maximum value that I should go to in this loop. It's not great. So ideally, let's get rid of this. The good thing is it's actually not that bad to do at all. PyTorch has some built-in code that'll help us with that. And that code is in two classes, so data set and data loader. Think of data set as kind of your fixed data set, right? Like a spreadsheet or something like that. Then data loader is something that lets your model iterate through that data set. Okay, so we're going to look at data set first. Here we're using PyTorch's tensor dataset. In practice, you might not do it this way. There are other things in torch.utils.data that might be convenient. Look at the docs or look up how to make a custom dataset if you need to. But basically here, we're just going to use the constructor and we're going to feed to it as input our X training data and our Y training data and store it in a single variable, train ds for dataset. Okay, so the first convenient thing about this object is that we can actually slice into it and get both our X and Y data with a single slice. So here we're going to get the third batch. So starting from, we're doing zero-based indexing, so starting from the second multiple of our batch size. Okay, so here, I don't know, this is probably not going to print anything nice. Maybe I'll just do it like that. Okay, so basically we have 50 rows of our data set, right? If we do yb.shape, it's going to be 50 by 1. So that's kind of nice, although not a huge improvement so far. You might not be blown away by that. But it doesn't really fix our problem from earlier with the batching. We're still doing this weird batching logic. But the way we can fix that is by using this magical thing called a data loader, which, like I said, basically takes your data set and lets you iterate through it a lot easier. Okay, so here is the line we used earlier to define a data set. Nothing new, I'm just repeating it to be kind of explicit. But the new magic here is once we've created our data set, we feed it to the constructor of data loader. And again, you know what, I'm not really being explicit enough with our variables. So here what I'll write is data set. That's the first parameter to our constructor. Batch size, okay, I've already specified that. So for example, batch size could be 50. That's what we have it set to right now. And then shuffle set to true basically just means randomly shuffle the order of our data set, which is a good thing for training so that you don't overfit to the specific permutation of your data that you have right now. Okay, so you just have this data loader class that we feed as input our data set, and then our batch size that we want, and it's going to handle all the batching logic for us. Okay, so we've defined it that way. And this is going to make our training loop way easier. So here's our new train function. For reference, this is the one we had earlier with all this nasty batching logic. This is what we have now. Okay, so same inputs as before, except actually batch size is no longer an input. So we take as input our model, our loss function, optimizer, and epochs. So that's all the same. But now we just feed as input train data loader. So no need for X train, Y train, and batch size. All of that is kind of encompassed in a single variable, train DL or train data loader. And then how does our loop look? So it goes through the epochs like before, and now it's just automatically batched using our data loader because we told the data loader we want batches of size 50. So when we do this, basically each iteration we're getting a new batch of 50 x values and 50 y values. Okay, we move them to our device, we make a prediction using our model, we compute the loss dot backwards, optimizer dot step, and then zero out our gradients. That's all we do. This is a full training loop, and this could apply for any kind of complexity of model. Okay, there are a few extra bells and whistles we could add if we want to, but if we just strictly cared about training our model, this would be fully sufficient. Okay, so let's define that. Again, I had this comparison with our old loop. So here we can actually see them side by side. You can see the code is a lot shorter and also just a lot easier to read. So the data loader really does make a big difference in terms of readable code. Okay, the note I have down here is just telling you basically that there are a lot of built-in data sets in PyTorch. We'll see an example of that in a little bit. But a lot of the time, if you're using a custom data set, you're going to have to make a custom data set class and also feed that into a data loader. Okay, so there's an article here by PyTorch that you can read about making a custom data set. And probably an LLM could easily do this for you too if you want. Okay, now the final thing we'll add to our training loop, so we're going to make it slightly longer than how it is here, is just validation loss. Okay, so we're going to compute a validation score after each epoch to measure our progress as we train. So basically all we're doing here is we're slicing our data set now into 3 different parts. Instead of 2 earlier, we said train and test. Now we have train, validation, and test. So let's run that. And we're just creating a data loader for each one. We're making the batch size bigger for validation and test because those aren't involved in gradient descent. So we can just make kind of bigger batches without affecting anything about our training. Okay, so our training function is basically the same. The new stuff we just added is this. We temporarily put our model in eval mode, and here we're just computing the validation loss every 100 epochs. Actually, what I'll do is, let's do it this way. This will make the output slightly cleaner. Okay, so we're going to train. Initialize our model like before, move all the parameters to our GPU, create an optimizer, and then train. And again, we're going to see the progress using this TQDM loop. Okay. And so now what's happening is our model, okay, I guess I got the logic slightly off for when to print the validation loss, but we're just seeing the validation loss every, 100 epochs, I guess? Yeah, every 100 epochs. And printing it to the screen so that we can monitor how well our model's doing. Validation loss didn't really change much. It was always kind of consistently low. I suspect it just means that the model was already really good, so there wasn't much room for improvement because this is a pretty easy data set to fit to. So let's visualize what our model looks like. It should basically be the same as all the other times we trained it. We're just using a kind of cleaner training loop with our data loader and data set stuff and a validation set for this loss. So if we run this, we should see something pretty similar to what we saw earlier. Oh, and we don't. Okay. What is happening there? So our model did not learn a great decision boundary. Something to keep in mind is that parameters are randomly initialized. Okay. So it's not unreasonable that this model actually did a little bit worse than the other ones. This decision boundary is definitely not as clean as before. So let's just try actually seeing what happens if we rerun this exact same code and train it again. Another thing to keep in mind actually is that I've split, we have less training data here, right? In fact, that's almost definitely the reason. Let's see what happens if we train it again, but I believe the problem here is that we have less training data than before because now some of that data that used to be dedicated to training is now used for test and validation. Okay, our validation loss is worse than last time. Okay, model.eval. Okay, so we get a much better decision boundary this time. So I guess it was just unlucky weight initialization. So this looks a lot better. Still actually not as good as before, but that has nothing to do with the code we wrote somehow being worse for training. It's actually a lot nicer for training. We just got less lucky. Okay, so finally for this last part, we're just going to tie everything we've seen so far together and see what it looks like to actually use PyTorch, because you might be a little bit confused. I kind of did a lot of iteration to improve what we were doing step by step. Let's see if you're actually, if you're actually using PyTorch in practice, what your workflow might look like. So let's just look at the key findings of what was useful and then see how we implement that. So the big thing that we learned was that PyTorch uses AutoGrad to automatically compute gradients, right? That makes your life a lot easier for backpropagation. The next thing we learned is that you have to tell PyTorch what device to put the tensors on, right? And in particular, if you're running on a GPU, you have to be explicit to move all your tensors to the GPU for faster computation. And as an experiment, if you're curious to see the boosts in speed, try running some of this code on CPU and then GPU and see how much faster it runs. To be fair, this code isn't very intensive in the first place, but as stuff scales, it's going to be more and more visible. Okay, we had torch.nn.functional that gives us built-in activation and loss functions. Our network inherited from this module class. We optimize our weights using SGD or Atom or any algorithm we want using the built-in optimizer from torch.optim. And then finally, we should wrap our data set in a data loader to handle all the batching logic for our model. Okay, with that, let's look at an example of the MNIST digit classification dataset. So this is a super famous dataset, basically consisting of a bunch of handwritten digits. And the idea is we're going to train a model to be able to identify the digits inside of an image. Okay, we're going to use a convolutional neural network, which you've hopefully seen by this point. If you haven't, it's okay. It's more about the general workflow here than the specific architecture we're going to use. Okay, but this is our data set. All of these digits are represented by matrices of ones and zeros, maybe not just ones and zeros, maybe there's some gray in there. So numbers between 0 and 1, let's say, representing the pixel intensities. And the idea is our model should predict that everything in the first row here is a 0, everything in the second row is a 1, then a 2, 3, 4, 5, etc., etc. Okay, so the first thing we're going to do is load our data set. And for this, we're actually going to use PyTorch. PyTorch has a built-in MNIST dataset. So I just wanted to show an example of what that might look like. So we do Torch Vision. Torch Vision is part of PyTorch. Torch Vision datasets.mnist. Okay. And so what do? Here we're saying store it in our. Or actually, I think this is saying get it from the data folder. Get the training portion of the dataset, download it, and then here we're just saying turn each image into a tensor so that we can use it in our neural network. And then for our validation dataset, we're basically doing the same thing, except instead of train being true, train is set to false. And actually, for some reason, download is, I don't know why that's set to false. Download equals true. Let's hold on. What's going on here? Okay, hopefully that'll run. We'll see. There might be some indenting issues there. And then we're just taking these two data sets, right, and wrapping them in data loaders. In fact, we can actually delete that and just write it like this. We're shuffling, setting our batch size. Then we're doing this thing called pin memory that basically makes it faster to move stuff to the GPU. Is it going to run or is it going to be mad? Okay, so it loaded everything. Good stuff. Let's take a look at our data. So we're just going to look at the first X and Y values in our data set, print out the shape and the values. So it's a 1 by 28 by 28 image. 1 means the number of channels. So in an image, RGB images have 3 channels. 1 channel for the red color, 1 channel for the green color, and 1 for the blue. Here we just have 1 channel, which is grayscale. So basically the pixel intensities are either black, the darkest they can be is black, and the lightest they can be is white. They can take any value in between. They're 28 by 28, so they're square images. That makes sense, right? These are square. And the first Y value in our data set is 5. So that means, actually the first handwritten digit, this is a mistake. Oh, no, it's not, is the number 5. And so here I'm just using some code from matplotlib to display what our drawing looks like. So let's see. So it's this. So it's the number 5. We're going to train our model on a bunch of stuff that looks like this. Okay. So here I'm going to use, I'm going to define a class. It's going to inherit from torch.nn.module. In our init function, we're going to run the constructor of nn.module. And then our layers are going to be slightly different from before because we're doing a convolutional neural network. Here we're doing conv2D. This is a 2D convolution, which you can see more information on here on PyTorch's website. I'm not going to get into the details. Don't really worry about the specific choices of layers I have here. That's not really important. It's more just the general kind of logic of how you define a class in PyTorch. So we're going to do some convolutions. We're going to have some dropout layers. Then we're going to have 2 linear layers at the end. So this should, this should look like a standard convolutional neural network. So basically what we're doing is trying to find an example that kind of looks like what we're doing. I guess it doesn't really matter. Let's do this. Okay, so we're doing a bunch of convolutions here. And then we're flattening the output, and we're going to feed it to a neural network. So this part here corresponds to these linear layers at the end, and this conv stuff corresponds to these convolutions here at the beginning. Okay, and you can read what each input here represents on your own later. Again, this isn't really critical, but it's useful stuff to learn. Okay. And then our forward function, this is kind of a poor way of defining things. You can actually, which I haven't shown, but if you're curious about it, you can use this thing called maybe if it's sequential. Yeah, nn.sequential to make this all a lot easier. Anyway, basically we're just feeding it into first convolution, applying ReLU, second convolution, applying ReLU. ReLU is an activation function if you haven't heard of it. We do some max pooling. We're going to do some dropout, flatten it, feed it to our fully connected layer, ReLU, dropout, go to another fully connected layer. And then we're going to do log softmax, which is kind of like softmax at the very end. Again, don't really worry about what this network is. The point is the general flow of this code. I defined an init function and I defined a forward function. Okay, that's the important stuff. Forward is the forward pass for the network, and init initializes our network. Okay. We already defined a loop earlier for training. No need to change that. That was great as it was. And the rest of the logic is basically the same as before. So we define our model, or we instantiate our model, I should say. We move it to our GPU. We initialize an optimizer. Here we're going to use the Atom optimizer, which is basically just better than stochastic gradient descent. We feed it as input our model's parameters. In this case, there are a lot more parameters, right? Because we have a convolutional neural network, we have our kernels, we have our fully connected layer. It's getting complicated, so it's really convenient to just optimize like this. We feed it our learning rate. Our loss function is going to be negative log loss, or sorry, negative log likelihood loss. And we're just going to train for 10 epochs. Why 10? Because I know it's going to work well at 10. Of course, in practice, you're kind of just going to have to figure that out on your own. There's no kind of magic number, but oftentimes it's probably at least a few hundred, if not even 1,000 something epochs. Okay, so we run that code. Our training code is going to be quite slow because, first of all, we have a lot of data. We have something like, what is it? Well, let's just see. Length of, what did we call it? I think train data loader, train loader. Actually, we'll do train data set. So let's see how many rows are in our training data. 60,000 rows, 60,000 images, right? And we're doing 10 epochs, so 10 times 60,000 data points will be seen by our model. So each epoch is going to be a lot slower than before. Well, training is going to be slower than before, and each epoch is also going to be slower. Okay, so let's train. It's going to be kind of slow. And just, I guess, while this trains, I'll give a little explanation of what we're doing later. So, okay, we just did 10%, so we just did one epoch. We're going to take our model for a spin. So basically, we're going to define this function here that computes the accuracy. Don't worry too much about the logic there. Spoiler, last time I did this, it got 99% accuracy. We'll see if that's the same. And then we'll visualize our predictions and see what we get. Okay, so we're about 50% of the way there. A little bit longer. I'll probably just cut this and go to the part where it's done training. Okay, our model is now done training. It took, what, a minute? Not bad. Let's define our compute accuracy function and see how well it does. Hopefully it'll be 99%. Maybe it'll be a bit worse. Again, like we saw earlier, the model we get is dependent on our random weight initialization, among other things. So we'll see if we end up with the same thing. Compute accuracy, indeed, 99%. Pretty good. Now, this is a function that's basically just going to print out a bunch of random points in our data set, random images in our case, and show the correct answer versus the prediction that our model made. We're probably going to get all of them right. It's only 10 images, so let's see. Yeah. Okay, so basically if the color is green, it means we got it right. So we got everything right. Just out of interest, let's change this to 100 images. I don't know how well this is going to scale. It probably won't scale well. Maybe it won't even work. But hopefully with 99% accuracy, like one of these will be wrong. Of course, that's not a guarantee, but maybe. Nope, didn't work. Okay. Oh, it's because our batch size is 64. Is that why? Whoa. Okay, no, it actually did. Okay, that's fine. So 10 it is. Okay, so our model did really well. Okay, now one final note. So hopefully, well, actually, before we move on, hopefully that workflow makes sense. It's not too much. Basically, you get your data set, which is what we're doing here. I guess I forgot. I wrote step 1 there, and I never wrote step 2. So step 2, define your model. Make sure that your model inherits from Torch's nn.module. Make sure that you run this at the start of your function, your init function. Method, sorry. So do all this stuff, define all your layers here. A nice thing actually is you can just wrap this in. Just gonna do like nn.sequential here so you can see what it looks like. So in the future, I would recommend using sequential. So basically what you can do for sequential is you can just write a list of everything you want your model to do, like this. And then you can just run everything in a single execution. Anyway, this is something worth looking into later. Anyway, so define all the layers and stuff that you need in your model, activation functions, blah, blah, blah. Define your forward function, initialize your model, initialize your optimizer, define your loss function, number of epochs, and then train. That's kind of it. But there's one crucial step I ignored, which is once you're done training, especially if it's really computationally expensive training, it's worth saving your weights, right? Saving them to a file so that next time you can just load your model up. So that's what I'm saying here. After training a big model, it's crucial that you save your weights so that you don't have to retrain it again, right? You might have gotten really lucky too, again, with your weight initialization, or you got a good configuration of hyperparameters that led to really good performance. So to save your weights, you first define kind of the name of the file or the path of the file that you want to save it to. Conventionally, you usually put .pt as the file extension. I don't think it's mandatory, but you might as well to remember pt, PyTorch. Then you just do torch.save, model.stateDict. So this is a dictionary with the state of the model in it, and then save it to this path. Okay. So this is the API for that, if you're curious. So we can save it. It runs. I don't know if anything's going to pop up. If we go here, basically we have this file here, probably not human readable. Yeah, okay, I'm not going to do that. But anyway, you have a file there if you want. What is this? I don't know what this is. Okay. Anyway, so you can do that. You can save it to a file. And then if you want to load it later, you just initialize your model using that class we defined. And then you do model.load stateDict, right? Because we saved the stateDict earlier. And then we can do this, and then we do model.eval. Then our model's ready to go. So that's it. I know that was a lot. There's a lot more to PyTorch that I haven't shown. There are cool libraries that go on top of PyTorch, like PyTorch Lightning, which makes training even easier. This is PyTorch Lightning. This is what we used when I was at Mila. If you're curious about that, I'd say learn PyTorch first, and then you can check out PyTorch Lightning to understand why it's nicer to use Lightning. I think that's about it for this. Hopefully this will help with your projects and your assignments. Yeah. So see you all at the next lecture.